Thank you. It's a great pleasure and a great responsibility to be able to speak in front of you today, a responsibility which I take seriously, and I hope to convey the information that I've organized to you in an effective way where you can see not only where the field is right now, but you can understand what has taken place in the past to bring it to where it is today. And I'm going to put a little bit of a focus on some of the commercial aspects and kind of the contemporary commercialization of this technology, which is really leaving the research lab and kind of entering into this commercial realm. The title of my talk is Quantum Computing Status and Prospects. And what I will do in this talk is the first part will be me speaking to you, and then after this part has concluded, which will take roughly 50 minutes, I will open the floor up to have an interactive discussion and to do a question and answer session. The outline of my talk is, in the first part, I will talk about the basics of quantum computing, and I'll focus that more towards a business professional or towards the lay audience. Now, there's many of you in the room, I notice, that are actually taking the technical course, and so there's no shortage of technicalities in this topic, but for today's lecture, there will be no equations. The second part of the talk will be an overview of available quantum computing systems. Okay, right now there's different classes of quantum computers that are currently available by these large tech giants, and we'll present a short overview of those and explain some of the key differences and some similarities between those. Right now, okay, one of the biggest questions people ask me is, what are the current markets? Okay, where is quantum tech being sold right now? And importantly, in part 4, we'll talk about the future markets. Now, I'm not a businessman, I'm a scientist. So I'm really doing this for the first time because there isn't good market analysis available of these topics. So if there are people from the business side listening to this talk in Russia, please do good market analysis, provide this data, and this will help, I think, the field tremendously. And I think that this type of audience, we might just have that type of person that sees this. So that's a real good area to contribute right now. And in the end, I will conclude, before opening this up to a question and answer session, I will give you the current status of quantum computing in Russia, which is where we all live, and so it's very important to us to hear about that. So what does a business professional need to know about quantum computing? And I believe today, right now, there's not one CEO of a major tech firm that has not engaged in significant discussions, many of which have decided to open up R&D efforts directed at quantum technology in various capacities. Moreover, I do not believe that there's one startup company that works on, for example, deep learning that has not considered, hey, do we need to look at this quantum technology? Do we need to try to target these new devices? Okay? So what do these business people need to know? Conceptually, here are the ingredients that makes a quantum computer different. There's 2 of them. In the classical world that we live in, so I call this world the classical world. And what that means is that, after millions of years of evolution, our minds have become used to things behaving in a certain way, such that when you throw a ball, your brain instantly says, okay, where's that ball going to land? You try to make a prediction of the future, okay? Somehow your brain is quite familiar with, you get used to things. You can go outside, you kick a soccer ball, you know where it's going to go. You get used to the physics of your own world. You open a door and you just kind of like let go of it and it stops right where you want it to. So these are the physics of our world, and these are a product of us learning about our world. Now, that's what we call intuitive. Okay, the things that we're familiar with, we call those things intuitive. When we shrink down to the micro scale, many of these things that we find intuitive, that we find every single day, the ordinary is no more, okay? And these very peculiar features of mechanics at the micro scale start to take over. And one of the more bizarre features at the micro scale, and there's many of them, and there's many consequences of them, okay? One of the more bizarre features is something called quantum tunneling. And let me explain how that works. So speaking of a ball, okay, it's a good example. If you take a ball and you throw this towards a wall, it's going to bounce back at you. Why? Well, because the energy of the ball doesn't have enough energy to knock the wall over, right? So it bounces back. That's great. That's, many games are based on that. But in quantum mechanics, it's different. This quantum mechanical particle, when it hits an energy barrier, will both reflect back. Is that okay? We're doing a little bit of an audio adjustment over here. So a little bit closer. So this, okay. Thank you. So we'll throw that ball, that quantum particle hits that barrier, and it does two things, not one or the other. It does two things. It bounces back, and it goes through that wall. Okay? So we call it the quantum zookeeper paradox, the lion keeper's paradox, right? So if you have a quantum lion, you put it in a cage, you have a problem, because this lion can stay in the cage and get out at the same time. And so this is the effect of quantum tunneling. And you'll see on the graph that I've provided on the slides, you have this in a red line, you have this idea of this quantum jump, or you have this idea of a thermal jump, which you think about if a particle is in that local well where those two lines, the blue and the red line, start, that particle can either jump over, which is a thermal jump, which is what we'd expect from the classical world, or it can hit what's called a resonant point, and it'll jump through that wall. The quantum computer will utilize this effect to try to find the minimum of some energy landscape. An energy landscape such as the drawing there will often be given as a computer problem, and the idea is to find the lowest point in that energy landscape. So quantum mechanics allows us to use this new mode of operation where we can find a local minimum and potentially jump to go to an even, lower minimum. And actually, if there are questions during the talk, that is okay, that is acceptable, depending on, I think that's kind of, we're sort of, I'm more of a dictatorial person. I don't like these round tables. It's more of a, I want to be in the end of a long table, but okay, we'll do the round table. So if anyone has a question, just kind of pipe in. The other effect, which is similar but slightly different, which you'll often hear about, is quantum parallelism, quantum entanglement, okay? This is really a core effect in the gate model quantum computer. And the idea there is that you can take a register, a quantum mechanical register, which is a memory storage device, okay? This quantum device can store the typical zeros and ones that a regular register, such as that in my telephone, can store. But there's a difference. These particular quantum mechanical registers can store superpositions of classical binary states. Not one or the other, okay, not 0 or 1 with some probability, but 0 and 1 at the same time, concurrently. And that is very bizarre, okay, and that has a number of consequences. That's at the nature of contextuality, non-locality, quantum spooky action at a distance, etc. And that is a resource that we utilize as quantum computing programmers. That is a resource which we study as condensed matter physicists. So what are some of the directions that leading quantum tech companies are taking today? Now, the interesting thing is about 3 years ago, talking about programming a quantum computer was kind of talking about going to Mars, okay? This is maybe something that's good for humanity, maybe something we'll eventually do, but really not something that is kind of outside your front door when you get up in the morning and something you're going to just go and jump in and head off to Mars. Now, what happened is these big tech companies, they built medium-sized chips, and they're very noisy. And this really opened up the awareness to the fact that we really don't know that much about how to program these devices. And although there's over 400 research groups in the world working around the clock on building actual hardware for quantum computing, the number of people that work on quantum software, in terms of the quantum computer algorithms, such as myself, is much, much fewer, much, much smaller, actually. And so these technological companies.
Jacob, do you understand me, or you need to only English? На русском нормально будет? А как определить, какой тигр реальный, в клетке или за клеткой? И кто определяет эту реальность?
So this question is coming about 5 or 10 minutes late, so I'm going to handle it at the end of the discussion. So if you have a question that's about what we're talking about now, then ask it. But if it's very late, then we'll start to go back and forward, and then this one sounds more like a philosophical, thing to handle later. So the directions that these leading technology companies are taking today, they're all different. They all have their own unique specialities. And we're going to talk a little bit about those right now. So the most famous companies right now in terms of quantum computing, everyone's heard about Google, okay? And they're focused on what's called quantum mechanical supremacy. And I'll explain that briefly. IBM, on the other hand, who really has developed, I would say, the biggest portfolio of serious research on the topic. They've been doing this for a long time, and they have some very good science that's come out of their labs. They're focused, I think, primarily on chemistry and quantum simulation calculations. D-Wave Systems, which does not make a gate model, in contrast to the other two companies which we first have mentioned, D-Wave Systems is working on optimization and quantum-enhanced machine learning. Their quantum computers are not gate model quantum computers. Those are called quantum annealers, and those are a little bit different. They utilize the effect of tunneling, where the other two computers, stakeholders, Google and IBM, they try to utilize the effect of quantum superposition and quantum entanglement as the fundamental ingredients to their computers. Now, everybody hears about, the frictionless ice skater, the fully error-corrected quantum computer, and that's the eventual goal. As we go there, we have to use error suppression techniques to mitigate, unwanted errors and unwanted noise. Roughly speaking, the more noise that a quantum computer has, the less like a quantum computer it will be. Noise seems to break quantum mechanics. It seems to break the effect of tunneling. It seems to break the effect of superposition. And the trouble is, at the micro scale, there's a lot of uncertainty in manufacturing. There's a lot of uncertainty in control because things are very, very small. And so we think now, and we say, that this is the second quantum revolution. The first quantum revolution took place over the last 100 years, and it gave us everything we have now. That was understanding matter at the larger scale, the medium scale. Being able to say, look, I can control things enough to make a transistor. Okay, I can control quantum mechanics enough to make a laser. I can control quantum mechanics enough to understand the LCD, this monitor in front of me. Now, the second quantum revolution is about controlling very, very precisely an extremely small quantum system. Not thousands of particles at first, but just how well can you control 3 or 4 particles? Can you control them perfectly? Then can you control 100 particles? Okay? Controlling 100 particles actually is above the world record right now. It's very difficult, depending on how much control you need. If you don't need very much control, then we can control thousands. But if you want very, very, very precise control, that's the second quantum revolution. And that's what everybody's working on right now. It's all about controlling with the highest amount of precision possible these very small systems. And in that regard, you'll look at what Google has where the trajectory of not just Google, but the gate model devices are doing. We don't know as much as we claim, as much as you think we'd know about the state of quantum computing. We don't know certain things which are actually quite fundamental. We don't know when we will be able to do something with a quantum computer we can't do classically. There's different speculations on that. We don't know exactly what are going to be the best near-term applications. Again, there's a lot of speculation on that. We're right at the threshold where these devices are now competitive with some of the larger computers if you're constraining them to very specific kind of impractical questions, okay? And that's a really interesting time to be. Right at the threshold before these things really do something, you can definitively say, look, the classical computer is unable to compete at this simplified kind of, particular task. And I'll talk a little bit more about that. So the really common one is to say, all right, and it sounds silly, you take your quantum computer, you do a sequence of random operations, and you say, well, your classical computer can't simulate those random operations. Now, why would you want to do this? Well, it's a game, it's a race, it's just a game. And then they call that quantum supremacy. So that's really the first milestone that most people would agree we're really close to that right now, and there's a lot of evidence to say that. Going a little bit further, what we have to do is we have to get the noise levels down. We have to be able to control those few quantum systems kind of perfectly, and then eventually we start to add more and more error suppression, and we end up with increasing the runtime of the quantum processor. So as noise accumulates, as time goes on, there's entropy, there's uncertainty, there's noise, and it turns out that you're only able to execute your quantum algorithm currently for a very short period of time. So it's like we have a quantum computer, but we can only use it for a couple seconds. And we'd like to increase that by hundreds or thousands of times past what is available today. And in doing so, it's a real race. And the direction of Google and these other people, right now everybody's still about under 100 qubits for Google, and we'll see where it goes. And it's not just a matter of saying, okay, how many qubits can you get? It's really a matter of saying, how well can you control the qubits that you do have? Now, it was Paul Dirac, actually, one of the founders of quantum mechanics. He said, oh, wow, there's this Schrödinger equation. If we could solve it, we would know everything about chemistry. And this is in principle true, but if we can solve it, can we solve it? So one of the biggest questions that is in theoretical quantum computer science right now is to say, well, can we solve the Schrödinger equation efficiently? So there's this idea, okay, it's called the Church-Turing Principle. And it says that every physical process in the world can be simulated using a computer. Okay, but not quantum mechanics. Quantum mechanics cannot be simulated efficiently in all cases unless you have a quantum mechanical computer. Fundamentally, most scientists in the field believe that quantum mechanics offers computational superiority over classical computation. This fact, however, is based on empirical evidence. Contrary to many of the things that we hear, we don't have definitive proofs for this. All of our complexity theory results for quantum computing are with respect to toy models and empirical evidence. I believe the evidence is great, and I believe these toy models illustrate that we will expect this and we will see this. Now, the question again is this: can we as human beings, classical entities living in the world that we've all evolved and we've all become accustomed to, can we physically solve these systems? Can we build computers to solve these systems? Is there something fundamentally different about quantum mechanics that stops us, like a physical law says, oh, the complexity to model that using a classical computer is too great? Is there something that's stopping us? Well, up until today, at the time of this lecture, as far as I know, every single algorithm on a classical computer that simulates a quantum system will blow up exponentially, okay, in time or in memory. That exponential time or memory is a very powerful stopping block, saying we're not able to simulate all of chemistry. We're not able to simulate all of matter. When matter and chemistry behaves quantum mechanically, it seems impossible for us to simulate it. However, a quantum computer, such as we're talking about the IBM quantum computer right now, is being designed to utilize quantum effects to simulate those quantum effects. And one of the most interesting things, and it's very frustrating, you say, well, do you understand quantum mechanics? Okay, not as well as I'd like to. Can you use quantum computers without understanding all of quantum mechanics? Yes, human beings will be doing that soon. And it's kind of interesting. It's a conundrum, a philosophical, like a bad omen. But hey, you don't have to understand it perfectly to be able to apply it. And that's kind of, I think, where we are right now. And it does seem, although it's not proven, that there is a physical difference between classical computers and quantum mechanical ones. And simulating matter and simulating quantum mechanical systems seems to be the first application that a quantum computer will be able to kind of excel at. And as we will go forward in this talk, we will say that the first applications of the quantum computer will be very much close to physics, because the quantum computer itself is governed by equations that are similar to the systems that they're trying to simulate. So that way they're easier to just kind of map back and forth. It's a technical thing. So now optimization, these are taken from a recent study. So what is optimization? And why is optimization different than simulating chemistry? That's a good question. So optimization is really what I think most of us think about when we think about computers. Most of us in our daily life, we don't think, hey, I'd like to simulate some condensed matter, or I'd like to simulate a quantum chemistry reaction or something. No, what we think about is we think, okay, look, I have a stock portfolio, or I'd like to do something a little bit better. I'd like to balance my checkbook, or I'd like to, look at my investments, and there's some kind of optimization, or there's decisions, and sometimes we make these decisions by ourselves. Sometimes we will go to a service and we will do, use data analysis to do it. And, traffic flow in cities, if you think of a smart city, this will be optimized in real time based on your current state. And these are optimization problems. These problems, we believe, are different than chemistry. These problems, we believe, are different than condensed matter physics. We believe a quantum computer will be faster at these problems than a classical computer, but we don't believe that it'll be exponentially faster, though still significant. Interestingly enough, the results of these types of studies do look good, and the interesting thing is this: many of the new models in computer science involve incorporating random processes into the computational algorithm itself. So for example, I create an algorithm to solve something and I don't use a discrete data structure. I use something that's a little bit fuzzier, something that has some randomness to it. And we find that these things work quite well. The good news about these quantum mechanical machines, such as D-Wave, these optimizers, they fundamentally have that randomness in them, and we suspect that they'll be able to tackle a wide class of problems. And potentially they'll be easier to program, actually, if you can believe that. Now, one of the most interesting arguments, which we'll get into a little bit later, is many tech companies have said, you know what, I'm just going to go quantum right now, because I need to invest all this money anyway into my software solution. I'm going to go quantum right now, and then that way I won't have to go quantum later. Okay, that's an interesting argument. When I actually heard companies were doing that, I was a little bit surprised. I said, well, maybe it makes sense. The interesting thing about this D-Wave chip, watch out for this one because it'll change the world. It's not D-Wave. There's Fujitsu, has 8,000 spins. It's purely classical. It's an Ising machine. Okay? It minimizes the energy function on a graph, the exact same model inspired by D-Wave. Okay? This thing's coming out this year. People have already used a prototype version. There will be an industry around these annealers. Some of these annealers will be quantum mechanical. Some of them will be purely classical. And some of them will be somewhere in between, like the D-Wave annealer. So this is a fascinating new model of computation, which is based on these interacting binary units called spins. This is the D-Wave stuff. And even without the quantum mechanics, these devices seem to be quite efficient, and they're able to solve a wide class of problems faster than many of the best computers today. And I think that the turnover point for these devices to really surpass simulated annealing, which is kind of their competitor, etc., on the world's largest supercomputers is really just a few years out, according to current estimates. So this is a very interesting area, and it's developing quite rapidly. Again, talking about all of these different, how many people how many people are taking part in this quantum revolution? How many companies have actually jumped in? Well, all the big ones, if you name them or if you search online, most of them now do have a quantum research activity. And, this includes everyone across Europe, and especially North America. And the applications seem to be quite strong for, different things in optimization. So this is what this is about. And particularly this slide actually will provide citations to the picture that I showed. So that picture is taken out of the citations there, and it gives it, some kind of overview of some of the current publications on the topic. So what is currently happening with quantum computing? So right now, quantum computing does not yet surpass classical computing. Okay, we're right in this fuzzy area where we're starting to see signs of that. So what kind of current markets exist for this? And you'd be surprised. Actually, there's, like I said before, there's already companies that are saying, look, I'm looking to the future, so I'm just going to put my application on a quantum computer so that way I don't have to worry about it later. Okay, so that's one thing. What else is happening? Okay, so first of all, let's look at the world and how they're spending money. And Russia is listed there. The U.S. is really the dominant global figure on quantum mechanical research. Depending on how you count it, their stuff is really even bigger than what's there. You can kind of see the numbers there. They're really quite huge. And then the rest of the world. So Europe is actually starting a multi-billion-dollar quantum flagship initiative. Russia now has the National Quantum Technologies Initiative, which I'm lucky to be not the leading role, but I'm playing a role in that. It's being led by Moscow State University, Sergei Kulik, who's, I think, an excellent researcher and an excellent experimental physicist who's done some very fundamental work on quantum optics. Very exceptional guy. This is a really competitive process to do these grants. And so the grant led by Kulik, our grant, this won in the end, and this will probably be starting in September or October. So that's something to kind of think about. And so the amount of funding that's going into this on the Russian side is increasing, as is the amount of funding from the rest of the world, and especially the big players like the US, China, Europe, etc. Even Africa has a quantum computing center now, and it's actually had one for over a decade. So the world is really seeing this as an opportunity. And one of the interesting things is people said, hey, this is kind of a bubble, right? Well, yeah, maybe, but it's interesting because a tech company, it's like a car company. You have a Porsche, right? You want to make a Porsche. You want to make a Ferrari. So what do? You make a racing team. No one gives a damn about racing. No one watches that stuff. It's garbage. It's just a bunch of waste of money just to do research, right? It's kind of the same thing. So a quantum computer is really an R&D kind of showcase, a flagship of these tech companies. It's like their race car. The better they can do with this stuff, the better they can control matter, the better they can control information, the better they can even wire these chips together, the better their entire understanding of physics and how to build things becomes, and it will influence their regular classical tech as well. And so, although there's like a lot of interest in quantum computing, I don't fundamentally think that the tech companies are going to give up on this any more than Ferrari's going to give up its racing team, which has never made it a penny. It's just an R&D thing. So that's my personal opinion, and I would, during the question and answer session, we can talk about what your opinion is on that. Oh, and just to go forward, and in terms of the side markets that are kind of emerging, there's a lot of different people that are kind of exploring techniques about refrigeration, about wiring. Actually, one of the most difficult problems of the quantum computer is how to get the wires to attach to it. This is an extremely difficult problem because you have to have hundreds and hundreds of wires, and these wires have to go down and they have to be 2 or 3 millikelvin, which is a really small temperature. Just being able to talk to that chip has pushed the wiring and has made like many different little startups to do different components for this. It's made Oxford Instruments, which is the world's leading developer of refrigeration units. It's made them rich, and it's made many different companies kind of spin off and offer different things from this. And we're also seeing now with the technology that we're using is superconducting low temperature electronics. Why? Well, the fabrication facility is not so different than the processors that we're all used to. So the reason why all of this stuff is happening now, one of the reasons why is because we have really good classical computing technology, really good fabrication, we have good control over it. The processes are different, the materials are different, but we still do things which are similar, and we're able to kind of bootstrap on that. And because of that, there's now renewed interest in, for example, can we make a low temperature superconducting GPU where we put a quantum processor next to it? And there's companies looking at that saying, okay, how can I make a coprocessor? Where's the field going to be in 5 years? Because once this quantum computer of D-Wave surpasses the world's fastest supercomputer for some small tasks, well, the bottleneck is to communicate with that thing. You have to send right now there's only a few of these. You have to send it over. Then eventually, even if you own your own, you're still going to want a GPU farm next to it. So it'd be really, it's really in the future of this technology, you'll see that we do need to put this control circuitry and processing units next to it as close as possible, and it'll have to be done at low temperature. And so we'll actually see really some big changes in the computer industry, and I don't think it's that far away. I mean, this is kind of, the snowball is rolling down the mountain. And it's one of the things where you can watch it go by, or you can kind of jump on it. Either one, it's going to be kind of fun. So where's it going to go in the future? And so everybody is saying something about quantum computing now. Even people that don't know anything about it. If you read what's in Forbes, it's just nonsense. Okay, Russian Forbes. These guys know nothing, right? And they're writing articles, a couple kids. And that's okay, because it's fun. But you also have to be serious, right? What do the real professionals say? What do the international players say? That's the question. Where do people think this stuff's going to be? And what is true and what is false? Okay? Are people just trying to rip you off when they say something, or are people trying to tell you some honest information? It's a good question, guys. So, of course, everybody's really excited about solving problems in material science. Okay? As we talked about before, chemistry, material science are big things. Portfolio optimization, machine learning, etc. So this is really where there is good evidence to say these devices will do something that classical computers are unable to do. And the future markets, which would be one of the ones that's probably going to be, I would say, more speculative, but I think personally will be transformative, is energy storage devices. This is an area where computational resources, where even the modeling, like how do you model these devices? If we could go back to first principles and really write down the fundamental equations, the quantum mechanical equations for these systems and solve them, it would revolutionize the world. I'm convinced of that. Energy storage right now is a major, major roadblock for the world, for all of us. It's going forward, but it's not going forward fast enough. And if we're able to, hit the reset button and look at things from first principles and, adjust our models and make these models pure quantum mechanical models and solve them. I don't know how far away this is in the future, but I do believe that the outcome of that process will be energy storage devices and new ideas and new technology that will be completely orders of magnitude better than what we have now. And so building a better battery, I think, would be really a good goal for a quantum computer, and I don't know how long it will take. But I hope to see something like that. And the interesting other aspect of this, in terms of the stability of the topic and the stability of the field, okay, is that we have a staggered plan for development. Optimization on D-Wave, as I said, it works without quantum mechanical effects. It works with just thermal noise. More quantum mechanical effects, it works better. It speeds it up. That gives you a roadmap to say, look, I can build a very large chip now, a very large processor, and I can just keep adding more quantum mechanics to it, and I'll keep speeding it up. And that's really nice. That's really a good advantage of these ground state computational devices, the annealing machines. That's a huge advantage. And it's a big advantage for people that make decisions at the level of a CEO, because they say, okay, look, do we have a roadmap? Is this just going to be something we try and fail and we have to give up? No. You can try and you can improve it incrementally and develop it. And that's, I think, something that's very, very core to this technology and really at the heart of it. And so as people look at this inside of Russia, as Russian business people make their decisions, I think that that's a key factor, saying, look, this technology will grow with the software. This technology will grow with the hardware. And there was an incremental path actually to go from the annealing devices that D-Wave has to a fully universal ground state quantum computing device. Okay, so it's a good one. And likewise with the gate model devices. The first thing these gate model devices will be used for, I believe, will be optimization problems. Those are easier to solve than quantum chemistry. So both of these approaches do have some kind of scalability built into them. Now, everybody talks about quantum crypto, right? The quantum crypto unicorn, the quantum crypto fear machine. Okay, quantum computers, quantum blockchain, it's nonsense. Okay, um, you know, quantum computers are not gonna like break your bank account. All right, at least not right now. So this is a little bit further out there. And what right now these devices are sloppy, they're noisy, and they're going to be good for simulation. They're going to be good to simulate chemistry. They're going to be good to simulate physics. They're going to be good for machine learning. Okay, cryptography is very discrete and very exact. And right now, the quantum computers that we have are very far from that. So there's no worry there. There are algorithms now that people are implementing that will make it so when quantum computers do exist, you won't be able to break cryptography. You won't be able to do certain things. So it's an area of research, I think, right now in terms of saying, okay, when will these devices actually come and do something with cryptography? But this is not going to be the early application of these devices. This is a later application. This is going to be after the battery is influenced, I think, or around the same time. So this is a late stage thing. It is an interesting topic to explore. It's more of a theoretical kind of thing at this point. So I don't think anybody, but it's a question I get all the time. They say, look, is quantum cryptography or whatever, is quantum computer going to, make everything I have online unsafe? It's like, no, it won't do that. Don't worry. And people have used this argument quite a bit to get money, okay, unfortunately. So now we get to the fun part. So what is the status of quantum computing in Russia? So people in Russia are very good at mathematics. They're very good at physics. They're very good at programming. It's one of the only places you can go. Like, one of the things I like about Skulltech, so I'm a professor at Skulltech, everybody in every department knows how to code. Okay, all the students can write a program. All the students are pretty good at math. All the students like physics. They like science. Okay, so it's kind of a cool place for quantum computing. I've done well with my courses there. Everyone from various different fields. I have biophysicists coming in there and saying, "Oh, I'm just interested in quantum computing. I want to take your really impossible course because I have nothing better to do in my life." Okay, come in. So what is the current status, and where can Moscow go? Can Moscow be a leading city for quantum software, for quantum computing? I think so. All right. So these slides are available on my website. My website is deepquantum.ai. If you're unable to find these, you can send me an email. So deepquantum, DEEP, quantum, quantum.ai. And these just list kind of the different stakeholders around the country who is doing different aspects of quantum technology. And mostly right now it's mostly on the research university side. Although there are players like Rosatom, there are some national labs that are now involved in this quite heavily. And in principle, Russia has done very well at small-scale experiments that are very exact. The overall size of the experiment is a little bit behind the state-of-the-art, but not that much behind the state-of-the-art. Russia's done very well on the analysis of devices, et cetera, et cetera. So the theoretical physics part, Russia's done extremely well on. The experimental physics part, I think, was not as well funded as it could have been. And so many of the shortcomings could be fixed with just having better equipment, although the equipment is actually not that bad. To give you an idea of what we can actually build, I'll talk a little bit about the MSU initiative in quantum computing. That's Moscow State University. And they're developing intermediate scale 10 to 50 qubit quantum simulators. Now, as I mentioned before, they have these, I'll go to the next slide. They have what's called an atom trap. And they can trap these atoms. Actually, they can trap more than 50 of them. Okay, so that's not a problem. But the problem is, how do you control it? And that's a really challenging thing. So even with 10 to 50 of these interacting particles, it's very, very difficult. So this is an ambitious project, but looking at being able to create some simple gates on 10, 20 qubits in the next couple of years is definitely within reach, and being able to have some minimalistic control over 50 is definitely within reach, and that's really where the state of the art is right now. So that is happening. That's ongoing research in Moscow. And for those people that are around Moscow, you can go talk to these guys. They're very friendly, and they have 2 laboratories. Okay, so down there you can see that Those are particles that they've trapped. The light spots are particles, and they're basically sitting next to each other. Now, the other type of technology at Moscow State University are these optical waveguides, and these are really cool because they build this on something that's quite close to a classical circuit board, and these are ongoing. The good thing about this is if you change the experiment, they can send this back to the university research lab, and they can make a new circuit board rapidly. It's just a couple weeks turnaround time, which is at the world standard. Actually, Moscow's very good at this. Moscow's very fast at this. In many different areas where they tried to start experimental labs in places in Singapore or in China, they realize that there's big gaps in their basic infrastructure, saying, "Oh man, we don't actually have anybody that does that in this country." So Moscow pretty much does have something for everything, and so the experiments can work here, and that's a very positive thing. Moscow is really, a very strong city for academics. There's many universities, and so you can find someone that is really one of the world's best at everything. Getting this all to work together and getting everything to kind of orchestrate, we will see. The National Technology Initiative starts in September, and there's over a dozen players in this across the country doing different pieces, and so my group is doing kind of the quantum computing algorithms for these devices. Now, the Skulltech work, as we said before, we're focused on, what are the limits of quantum computers? What can they not do? So it's kind of interesting to say, okay, my whole research career has been about what quantum computers can't do, right? Like, what is it not able to do? Why is it different than a stochastic process or a classical process? And then on the other side, the more optimistic side is, okay, now that we have those chips, you can watch the field transform into something you do not recognize anymore. When I started doing this, it was really like theoretical. It was just like, what does physics say about a computation? What does physics say? Because, a computer is not just some kind of isolated mathematical entity. It's a physical system. It's fundamentally governed by the laws of physics. Its limits, just like the maximum speed of something is the speed of light, its limits are governed by physics. So how fast can it compute this family of functions? How fast can it solve this class of problems? Okay, so those were the early questions, and now these guys have built this stuff kind of in the middle of my career. So I can either keep doing all of this theoretical stuff, or I can say, okay, look, how about we just try to program one of these and just see what happens, right? And that's kind of the direction that we've taken now. So you do have these theoretical groups that are now kind of looking at these applications. It's kind of a fun time. There's a little bit of bleed over between our work and the machine learning work. Some of the models of machine learning are actually quite close to condensed matter physics models, and they actually map quite naturally to quantum systems. Other techniques, such as something called tensor networks, which have arisen in quantum mechanics as a method to simulate, as a graphical language to describe systems, those actually map very closely to certain machine learning models. And so the challenge for me recently has been to say, look, the field is reinventing itself, so either you keep doing what you're doing, which is working fine and it's fun, or you say, look, I want to go take part in that new thing. I really want to see this stuff kind of, solve something practical, or, I really want to program one of these new chips. And so that's been really the drive of my research, over the last year at Skulltech, where we're saying, okay, look, let's go and let's look at these really contemporary questions, these contemporary challenges, coming at it from this more theoretical background, but having a practical goal in mind, an expected output where we can actually accomplish something using those processors to make a calculation. So that's where we are today. And so this will conclude my talk. I'm quite accessible. If people in the future, you're going and you're making these types of decisions, you can always talk to me and I can put you in contact with a pretty big network of different people in and outside Russia. And I hope now we can open up the conversation and we can discuss. The gentleman over here on my left had some question about the lion. It was more philosophical. But if you guys have questions about quantum computing, about the industry, about the lion, whatever you want, I think now is a good time to go over that. So I will leave it to you.
Jacob, so what about a lion? Is it inside of the cage, outside, or everywhere at the same time?
Okay, so the strange part is the fact that you can take a particle that has less energy than a barrier, and you can throw that particle into that barrier, and the particle can be measured on the other side of that barrier. And you can do other stranger things than that. You can take sophisticated experiments where you can make a particle interact with a copy of itself. Okay? The interpretation of that, there's no other way to say it. And I don't want to get it, I'm on the mathematical physics side of things. I'm not a philosopher, although I do think that philosophy does have an important point in science. It's just so bizarre, I don't know any other way to say it. A particle can be in two places at once for some period of time. Then those those copies of the same particle, whatever they are, I can't even put it into words, can come back together again, and they can interfere with each other. So it's very, very strange. I haven't really made sense of it. You can do the calculations, you can look at it. Interestingly enough, when quantum mechanics was developed, people thought all of this stuff for the longest time was just a weird mathematical artifact. So what happened is they took this wave equation and said, okay, here's a wave equation. And then some guy named Schrödinger, he got out the bound states of the hydrogen atom. Okay, there was no reason why this thing should even have bound states to begin with, but okay. Then he had this thing. And every single thing else about it, no one believed it because it was just sort of like this hand-wavy thing they just kind of pulled out of the sky based on some very simple arguments to begin with. It sort of fit. And then how much it predicted after that was completely unexpected. That little assumption they made at the beginning would actually turn into our most powerful and most predictive theory we've ever had. So all the math out of it, it was questioned and questioned and questioned and questioned. And everybody said, look, this is just some bizarre mathematical artifact. You have these complex vector spaces, you have these weird Hermitian matrices and all this like strange, these infinities and all these problems and blah, blah, blah. And the messed up part about it is the whole thing actually works and is true. Okay, it doesn't seem like there's much mathematical artifact past some strangeness, which is called there's some what's called gauge freedom. There seems to be some gauge freedom in the theory, but which is non-physically observable. But everything else has been really consequential, and it's been just bizarre. So I don't have a good answer for that.
The performance of quantum computers is measured in qubits, and recent initiative from IBM, they built 50 qubits computer. Google built 70 qubits computer. Do you think what's the technical limit of the number of qubits which is possible to fit in a single quantum computer?
So that's a very good question. So if you add error correction and you think about this, you can actually think about the physical size of the chip. And at some point, this thing becomes too big to really, kind of imagine. And I don't have the calculations right on hand for that, but I believe that based on everything, we're going to get some problems. We're not going to be able to get a very, very large chip, but we'll be able to get one of intermediate size. So remember, things that are very small, we can calculate easily. Things that are extremely large, have very weak correlation when we randomly sample between two things. Big data is not really extremely large data. It's medium data. Medium data is nasty because it's highly correlated, or can be, and it's big enough where we have to put this on some large computers. So I think that the area that human beings cares about is not the extremely, extremely large, because for extremely, extremely large problems, we do have analysis tools that can tackle those. We can take limits, we can make really simple approximations to say, look, let's assume if this is big enough, then this happens, in this data set. And the extremely small, we can just calculate by brute force. It's that intermediate realm, and I believe that the Google and the D-Wave chips will be able to hit that intermediate realm. And, it's hard to predict the future. Like if you showed your telephone to somebody 30 years ago, it's hard to predict the future. So there's always that guy or that girl saying, these old captions, someday a computer will weigh less than, 500 kilograms and be able to fit in your basement. So I don't want to be that guy. So I think there'll be some innovation that gets around it, I suppose. But it's the medium data that'll get you. It's not the really, really big stuff, in my opinion.
Jacob, I'm here. Explain again in short details, maybe how to, concerning to problem of quantum machine learning problem, how to write or learn this physical system of particles on some learning data set. How to write this data set into physical condition of the system.
Super good question. I can answer this question in a few different ways. So, number one, if I want to use a quantum computer to simulate a physical system, I have to be able to map that physical system to the quantum computer, and then, for example, measure something about that physical system. If I want to use a quantum computer to do something, let's say, make a classifier from machine learning, okay, which is I think what your question's more about, if I understand it. To make that classifier with machine learning, I have to be able to make this quantum mechanical computer represent, let's say, for example, a deep neural network, okay? Interestingly, there's two ways that this can be done that I've explored. One way is to use what's called a restricted Boltzmann machine, which is actually modeled after something called an Ising model from condensed matter physics. The Ising model happens to be what's called the free Hamiltonian of the Google and the IBM system. In fact, the D-Wave system realizes a tunable version of the Ising model, okay? So all of these devices are very, very close to this restricted Boltzmann machine, which is a model from deep learning. And the act of training is all about taking a pattern and making this model recognize the pattern by making it so the model will assign a low energy to that pattern. Okay? And so to give you a conceptual idea of how this works, so let's imagine we have 100 pictures of you. I'm sure the government has more. Okay? We take 100 pictures of you, we convert this into data that the quantum computer can read, and what we do is we minimize the energy for these 100 pictures at the same time. Then there's two things we can do. One is we take picture number 101 and we try to calculate its energy. And if this thing was trained correctly, it'll say, oh yes, this has low energy. The other thing we can do is we can run the device backwards and we can generate a statistical distribution of images. Although they won't physically look like you, they'll have statistical properties that are actually similar to you. So we'll kind of be able to use it in two different ways. And so the training on the training of the D-Wave machine is all about making a system assign a low energy value to a certain pattern, and you can do kind of other things, but that's the main gist of it. I hope it's clear. I'm trying to answer the question as clear as I can. So,
Jacob. Okay, we're just talking about one of the risks about blockchain, but what do you thinking about another risks? It's about dangerous from some weapons. Maybe someone can take that computer for another from another country, and there can be new war for the whole planet. And about the peoples, they can lose jobs because right now we don't have so much time to change our specialization for the new markets. But right now it can be more dangerous because the speed is so high. What do you think about it?
okay, so this is actually a very good question. One is about the military applications of quantum computing, and will this be used to harm? I think there's two microphones now. Okay. So there's two questions here. One is, will quantum computers be used to kill people? Okay. The second question is, will quantum computers take away our jobs? And these are both actually very good questions. So in regards to will quantum computers be used to kill people, we already have enough atomic bombs to blow the world up like 30 times or something. So we're already pretty good at that. I surely hope not. And I think in this day and age, if you look back at like historical indigenous populations, they had rules of war. So what do I mean by that? Okay, like Shaka Zulu, okay, in the south of Africa was famous because he said, hey man, F the rules of war. I'm going to come up with my own stuff and just kill everybody, right? Before his time, they used to line up, it was like 50 paces, and they'd throw rocks at each other or throw spears depending on how bad the battle was. Or maybe the two kings, the two tribal leaders, would fight to the death. This is common in Europe as well. This is common in North America. Why? Because life is too valuable. The whole society can get destroyed. But even today we have rules of war. You're not allowed to use a nuclear weapon. Okay? And so I think that we control ourselves as a society, and we control ourselves more and more going forward. And I think that on most people's minds, the applications of quantum computing are going to be very, very positive. I think that, you know, classical computers are probably more dangerous, and they've been used for much more than quantum computers will be. Then again, I don't know. I mean, we don't need more powerful weapons. We already have ones that are sort of too powerful based on our rules of war. Now, going into this other question about, you know, economics. Okay, so I'm basically a free market capitalist. You know, I'm kind of a libertarian, kind of live free or die. But at the same time, I like social programs. And I think that if you don't regulate your markets, bad things happen. Banks are bad. Banks are scary. So quantum computers, will they take away jobs? Will they change things? Yes. Are there many other things like machine learning that will change things and take away jobs? Yes. Does society kind of need to rethink itself at this point? Yes. Okay, are all these things connected? Yes. Will quantum computers make it worse or better? I do not know. But even though, you know, my generation in particular, we go from like this, you know, leave everybody alone and you be left alone. And then now we reconcile that with like the modern world. We have to have these programs to facilitate education, to facilitate society. And we kind of mix these two ideas together. I'm from kind of a faraway place, so the politics and kind of the viewpoint of people is very different. But having a safety net and making sure that people are okay is probably something we can do better with good computers than without them. And it's probably something that we can afford to do, actually. And, you know, what will the future look like? Will people just kind of sit around and learn stuff all day or do something? I don't know. But I'll tell you one thing that's really scary is if Google owns all the robots. That's a pretty scary world. So I don't know the answer to this, but it could be kind of a horror movie. So let's hope not.
Вы упомянули о квантовом устройстве для отжига. Вот хотелось бы узнать детали технические. Во-первых, насколько большое это устройство, которое в 2018 году, вы сказали, выйдет на рынок. Ну и что за компания его выпускает? Хотя бы какие-то характеристики, где посмотреть.
Okay, very good. Number one, search for Fujitsu Digital Annealer. Fujitsu Digital Annealer. This device, they claim, will be a classical annealing device, not quantum mechanical. What it'll do is it'll take this, basically a model of a graph, and it'll assign a penalty function to that graph, and it'll minimize that penalty function. This is a type of a constrained optimization problem. The Google machine will do the same thing as this. Not Google. Please strike that from the record. Late at night, 9 to 11. Okay. The D-Wave machine is an annealing device. D-Wave, D-W-A-V-E, D-Wave Systems Incorporated. It's in Vancouver, British Columbia. It's a Canadian company. They sell these quantum computing devices. Now, in terms of the size, the Fujitsu device, right now, I believe it's available with 2,000 classical spins. They're claiming they're going to go up to 8,000. D-Wave is currently in the prototype stage with the 4,000 spins, and it's accelerated by quantum mechanics. So these are really interesting. These are really interesting, and these will be the first really fundamentally different type of computer that's come out for a while. So all of our computers today sort of work with this kind of von Neumann, what's called a von Neumann type architecture. These devices are all about minimizing energy functions on graphs. So it's a very fundamentally different kind of setup. So Fujitsu and D-Wave Systems are the ones to look at. And after these things start to work, you'll get many more competitors. you would think.
Hello, I want to ask one question. You said about quantum computers have problems with special wires with low temperature. What do you think about adoption of this technology in future? How many years it will take with maybe existing, maybe developing materials to make some good wires? Because without wires, I don't understand how to build good systems. Thank you.
Well, they're doing some pretty impressive stuff now. So let me see if I put a picture in these slides. Okay, so it's a little bit hard to see. So what's in that box, right? So the wiring and stuff. If you search online, if you search for IBM-Q, they'll show you some of the wiring, and they'll show this like long, like multi-stage refrigeration thing. The wiring is challenging, but they are doing it. My point is that they are doing the wiring, and just being able to physically build that is a real milestone, I think. And it's not a milestone for quantum mechanics, it's just a milestone in general for humankind's ability to kind of make things. So I don't think the wiring challenge is their biggest challenge. They're facing so many challenges right now. It's a major challenge. So, in terms of how do they make that smaller, how do they miniaturize that, which I know would be better, I do not know how to do that. So we're kind of at the stage where it's really the beginning. And if you think about the tech industry, I don't know if you know this, but the transistor came out, and the first time people got a real big chunk of money to commercialize it is they said, hey, we can use it to make a better hearing aid. We can make an electronic hearing aid with this transistor because you can use them for amplification. And this hearing aid will be nice and small and can fit in your ear. And this funding, they got the money, okay, this big grant a long time ago. This spawned the use of those transistors to replace, the existing technology, which were these tubes. Okay, and so we don't really know where it's going to go. But I say if it's anything like the classical computers that we have today, it'll go fast, and there'll be unexpected turns in it. And I think that the wiring challenge and the hardware surrounding it is a really important thing, and especially for a nation like Russia, which does have all of this stuff, and they have very good talent on every little component. So it's something kind of important to say, okay, now we have this national technology initiative. Part of it is just to make better wires. Okay, why would you want to do that? Well, you'd want to do that because you want to have the infrastructure in your country to be able to, build whatever you need to build, and you never know what startup companies will come out of that. So I think that, as I showed the other pictures, looking at these chips coming out of MSU, this is easy wiring comparatively, but this will actually improve through the 3-year NTI, and the waveguides up on top are really interesting because these things will be, these will support like quantum waves. So this is just kind of part of it. So I don't know how long it'll take to really, see a huge advancement, but if they're already wiring for 50 qubits at IBM, I think that's already pretty impressive. And I think once we get up to a couple hundred qubits, we should be able to do some stuff with these IBM chips that would be very impressive. So I don't really know the answer to your question. So.
Besides quantum computing and quantum cryptography, are there any other use cases for uses of quantum technologies?
There's an emerging area called quantum sensing, which includes quantum radar, okay, of all things, quantum enhanced like machine vision. So interestingly enough, what they'll do is they'll entangle two particles, which is some kind of quantum correlation, and they'll send one of them out and then it'll bounce back. And this will give fundamentally different information than if they didn't entangle it. And using that, they're able to do things with radar and with vision, and also with sensing magnetic fields. And so, yeah, there's a ton of different. It's really like if you look at every device around you, every single device around you uses quantum mechanics at some level. It's just that we're not considering we're averaging it out. Okay, so like in a transistor, what we do is we make a model of that and we assume that quantum mechanics is maybe negligible or maybe kind of averaged out. We're not saying what's the first, what's the exact solution, what's the first principle. And we don't even know what's there when we look. So I think that there's going to be, a number of different unexpected things because, matter is very unexpected. It's completely nonlinear stuff. You never know what's going to happen. So I think there's going to be a number of things that will really change in the second quantum revolution. Where, again, going from the first quantum revolution, which was all about saying, let's get some basic control over a large system that's noisy. Now, the second quantum revolution is, let's get fine, high precision control over a small system that's not noisy. And so I think once we start looking at that, then we'll have not just quantum sensors, not just quantum radar, but every device around you will be fundamentally, modified by this revolution. So I think so.
Джейкоб, вопрос такой. Я человек новый вот в квантовых вычислениях, поэтому вопрос очень простой. Какие ожидания сообщества от развития квантовых вычислений вот через 10 лет? Что произойдет? Как это будет сопоставимо с существующими суперкомпьютерами, которые вот на существующих технологиях? И вот тот прогресс, который есть за предыдущие 5 лет развития, он подвигает нас к мысли о том, что через 10 лет там, мы дойдем до каких-то вот результатов, которые ожидаются, или пока путь разочарований?
So it might be from inside the field, it's moving really, really fast. From outside the field, it might be moving very slow. Maybe it's relative. So from inside the field, we had, I would say, we were stagnant. We had 5 to 10 qubits for a long time. And then suddenly they kind of got control over that. And now they said, okay, let's make 50 or 70, right? And so that happened very fast. This was really unexpected. And this was really just a couple of years ago. And I think that's kind of the turning point. That's really the tipping point. If you can pass 50 qubits with decent control, and I think that we're going to hover here for a number of years and really kind of get that under control. On the D-Wave side and on this annealer side, I don't think there's any messing around with that stuff. I mean, this Fujitsu chip, they paired it off against supercomputers. It's not even quantum, but it uses some physics to, it's a quantum inspired device. So I would say that, from my perspective, it's happening fast, and I don't think that it's going to slow down. And I think the first one to really go to market is going to be this D-Wave stuff. And I think, I'm going to put my word on it. And I think in 3 to 5 years, though, that class of processor will be crushing supercomputers at optimization problems. What to use it for, what the market is, I don't know. One of the interesting things about optimization problems is, where is the market? Airplanes land without quantum computers. Trains are routed without quantum computers. Where are the hard optimization problems? Okay, how are you going to sell it? This is another question. But in terms of benchmarks, I do believe that these processors will be crushing supercomputers in 5 years, really. And that'll happen because the devices from Fujitsu, the current generation is 2000, the next generation is 8, the current generation of D-Wave is 4, the next generation will be 8. Then after that, what is it, 16,000 spins? This is impossible to simulate. This is very, very hard to simulate. In terms of the Google stuff, on one hand, this might be like a race car team. This might be Ferrari's, race car effort for some time. On the other hand, we don't know. So if they got good control over 50 bits, it's very difficult. And I think you'd already be able to start to say, okay, look, what is the next direction we need to go to do something practical? And you probably need a couple hundred bits there or a couple hundred qubits that are very well controlled. I don't know when that's going to happen. I mean, as I said before, we were hovering around 10 bits for really a decade, and then this really happened a couple of years ago. So that stuff has been kind of that stuff was just sort of like, wow, Google's doing this. Where D-Wave is kind of went on a steady thing. D-Wave is like 20 some years old. They're just kind of doing their thing, right? Okay, we're going to make an annealer. We're going to make an annealer. So it's easier to sort of predict that because the past data is very very consistent. Google, I don't know, but from my side inside the field, it's really kind of shocking that if you would have said 3 years ago, oh yeah, IBM's going to put out a 50 qubit chip, they're going to let people use it, I would have been like, no way. So.
Jacob, another question. What do you think about new direction for the technology? What is the start for which direction? There is a for big data or maybe something other. What is the start for the technology? And maybe a few examples for that.
Awesome question. My audience right now, my audience is not very specific. It's not a very big audience, but it's very specific. And in this audience, I'd like to encourage you to do something. Let's make Moscow a place where quantum software happens. Go and make a startup company. You'll get some money. Go try to do it there's different projects around the world. Email me. I'm a professor. I'm not going to quit my job as a professor after I made it to be a professor to go make a startup company, but I'll help you do it. I'll talk to you. Make Moscow a place where quantum computing is happening. You can compete with Boston. You have the minds here. Like, we have everything here. We have a cool master's degree track on quantum computer science at Skulltech now. Let's make it happen. Let's make that quantum software here. Catching up with Google on the hardware is a little bit more difficult. The MSU stuff, it's more of a quantum simulator than a quantum computer. But let's make Moscow into something that is very, very good. And if your startup doesn't work, that's normal. You can go do deep learning afterwards because the skills are not so far. And in terms of that, I would say make a quantum software company using deep learning just to optimize something better. Make a quantum software company to do something with drug discovery, okay, or to do something with chemistry. Do this in Moscow. Be brave. Just do it part-time. Follow the passions. Because this is really what Moscow does not have right now. And it's the only major city in the world with this many universities, this many extremely highly trained technical people. But if you go to other cities, they have these quantum software companies now. And these startups are really going to be there. And so the interesting thing about it is, did you notice how each one of these companies has a completely different focus? That's a little bit strange, right? So no one really knows where the good market's going to be. But if you made a good platform and you said, okay, I'm doing deep learning for, I'm using quantum mechanics to accelerate, let's say, drug discovery, or I'm using quantum mechanics to do this, even your classical software, or if you put it on this Fujitsu chip, this stuff will be worth money. And, it's hard to make a startup company that's worth $0. And it's very low risk if you do it part-time. And what else do you have to do anyway? Do it. So I think it'll be up to him. So don't like clap at Moscow doing it, but somebody in this room has to do it. Make the startup company, and we really need like half a dozen of them. There's room for it, guys. Yeah, I will clap to this too. Like, please do make a startup company. Okay.
There is a good point for the finish.
I hope that you enjoyed the conversation as much as I did. It's obviously a lot of work to prepare this, and I actually don't like to speak so much in public, but this is really fun. And I hope that the outcome of this really is to see Moscow. We need regular people. We need regular computer people, regular tech people doing quantum computing. It has to leave the university. I can't be the one that does this, and my students won't either. They want to go do postdocs at like some Moscow State University or something. They want to go to some famous institute after they graduate with their PhDs. We need startup companies in Moscow, and so I hope someone either in this room or watching our live stream will say, hey, you know what? Why not? Why can't I just do a startup company on the weekends? And you can go out to Skolkovo and you can put together a pitch. There's regular things to pitch. Now in Moscow, they'll give you a couple million rubles pretty easily to get you started, put together all of the documents. And so I hope that's the outcome of this. And if not, it's okay. And if in the future, if you come across quantum computers, drop me an email if there's any questions, and I'll put you in contact with or try to solve your question as it goes. So thank you all.
Let me ask. Finally, yes. Will we ever see quantum processing unit on our mobile devices?
Xanadu, it's called Xanadu, in Toronto, Canada, led by Christian Wiebeck. They are trying to build a room temperature quantum computer. The chip in front of me right now is a room temperature small quantum computer, these optical waveguides. So in principle, we might not see this very soon, but in principle, it could probably happen at room temperature eventually. It won't be the first thing that happens. It does add an extra element of noise to the system. Most of these experiments are done at ultra cold, cryogenic temperatures. So eventually, yes.